It's a huge pleasure to have Adriano Aguzzi here at the IGC giving the seminar today. He's been making very important discoveries regarding transmission of SARS2 in the population, so we thought it would be incredibly timely to have him giving this seminar, and he was super generous to accept immediately to give this seminar. So Adriano Aguzzi is professor and director of the Institute of Neuropathology at the University of Zurich. And in the past 25 years, he's been studying the immunological and molecular base of prion pathogenesis, and to clarify the pathogenesis of the disease and to identify the cells and molecules that are involved in prion neuroinvasion. And I guess we can see some neurons behind him. He's the founder and director of the Swiss National Reference Center for Prion Diseases, and developed many diagnostic and therapeutic methods in the field of transmissible spongiform encephalopathies. And he has received many, many honors, 2 ERC Advanced Grants, the Robert Koch Prize, Ernst Young Prize. And the most interesting one that I've just heard recently is that when he got the EMBO gold medal, actually he got it in Portugal at the Gulbenkian by the Minister of Science, then Mariano Gago. So that was very nice to hear. He's been at the IGC and other institutes such as Champalimau many different times. He loves Lisbon, and we will be very happy to have him visiting in real flesh in the future. But it's really nice to have you here, and he is happy to be interrupted if you have questions. Thank you very much, Adriano. The floor is yours.
Right, so great, hello everybody, great to be here, and as Monica was saying, I mean, for me, it's always a great pleasure to be in Lisbon. This one in kind of a virtual reality mode, but it's always wonderful. So great to be here, and thank you for coming so numerous to my seminar. Now, this time I will be talking about our efforts on COVID serology, which is something that was completely unexpected and new, and it's kind of an experiment because I've never talked about this yet, and as Monica was mentioning, I have been obsessed with prion pathology and prion diseases for the better part of the last 30 years, and this is pretty much the only thing I did, and at some point, when I took a pledge. Several decades ago that I would only work on prions, and the reason for that was because as a postdoc I was very I was very easily distracted, and I was doing all kinds of things, and then many things didn't work, and so I was given the advice to focus. And then focus I did, and in fact, but now I broke this pledge, and the reason because I did so is because well, actually, what happened was that the university in late February closed down, and then they told us nobody's allowed to work in the lab anymore unless you do COVID research, then you're allowed. And so we thought a little about it, and we thought, okay, fine, let's do some COVID research. And so that was one of the reasons. And the second reason was that in the past years, I have been interested in immune responses against autoantigens, which are, of course, a pretty rare thing to happen. But the reason was very practical, and that is that antibodies can be fantastic therapeutics, and I mean, if you think of how the therapy of a lot of diseases has changed. I mean, the more than 50% of the revenues of big pharma is now antibodies, and so things have changed a lot. But antibodies have also a lot of trouble, and a very big problem that comes invariably is that repeated administration of biologicals leads to immune responses against the drug itself, and one idea was that if you derive antibodies straight from humans, those may be actually better tolerated on the long run. So one idea was, okay, maybe we can look for autoantibodies and perhaps we can clone them and see whether we can make some therapeutics out of it and characterize their specificity. Because the other idea was that, and this is very anecdotal, and maybe it's not even entirely correct, but the idea was that that the selectivity of human antibodies may actually be better than that of antibodies derived from other species or from synthetic libraries, and that the cross-reactivity to endogenous proteins might be actually lower. And as I said, I mean, the evidence is anecdotal, but you know, sometimes you start with some wishful thinking. So, but of course, autoantibodies are rare. You know, I mean, typically the human immune system is very good at suppressing autoreactivities, and rightly so. I mean, otherwise we all would be in trouble. And so then the idea was, okay, maybe you know, I was specifically interested in antibodies against the prion protein and some other proteins related to neurodegeneration, and there was no evidence that such antibodies would exist. So my thinking was that maybe we just need to test a lot of people, and if we really go broad, we may actually find something. And so, because I work in a hospital, in a department of pathology, I went to the head of clinical chemistry, Arno von Eckelstein, asked him, I mean, how many people are we actually drawing blood from at our university hospital? And it turns out that it's a hell of a lot. We have more than 80,000, somewhere between 80,000 and 100,000 blood samples drawn every year from inpatients and outpatients of the university hospital. And this, of course, encompasses also people from whom blood is drawn very frequently. For example, if you are in intensive care, you know, essentially blood will be drawn every 30 minutes for oxygen, partial pressure, and saturation, and all kinds of things. But even if you disregard the repeat samples, I mean samples that are taken at very short intervals, it's still more than 80,000 samples a year. And so I thought, okay, you know what? I want to investigate all of them. And that, of course, had some logistical challenges, because how do you do it? I mean, how do you handle this enormous number of samples? And that's how the whole thing started. And essentially what we did was to establish a largely automated robotic pipeline to look at serology. And maybe now I could show a couple of slides, and so let me see if this works. Right, here we go. You guys see something? Very good. So right, so that was the general idea of how to do this, and this is how this setup looks like. Now let me pull out this thing so that this is out of the way. Okay, right. So essentially, we have all kinds of university hospital departments, and they all end up in clinical chemistry. That's where the blood is being collected. And then the blood is used for conventional blood work, you know, clinical chemistry, you know, transaminases, glycemia, and hematology, and all kinds of things. And what our ethical committee has allowed us to do is that the patients can sign a so-called general informed consent, which means that they agree that if any residual material is left over, and this is almost always the case, it can be used for research purposes in a pseudonymized manner. Meaning, I should stress this, the pseudonymized is not the same as anonymized. So anonymized would be that you strip all identifiers, and then you end up with a blood sample that can in no way be reconnected to the patient. Pseudonymized means that each sample is given a hash code, and the hash code corresponds to a patient, and we, who run the study, will never have an opportunity to reconnect the hash code to the patient, but this in principle can be done under very specific conditions. And so this is the way this study was organized. So we have pseudonymized samples. And then essentially the only manual part of this exercise consists of taking the tubes as they come in, and then placing them into specially designed racks, which we have 3D printed and so on. And then these racks go into a small robot, a small Perkin-Elmer Janus robot that essentially very simply pulls out whatever is left of the plasma and transfers it to 384 deep well storage plates. And these are barcoded, and the material gets inactivated by solvent detergent extraction, which so that we can get rid of all viruses. This is more important for hepatitis virus, and because COVID, I mean SARS2 is not does not induce viremia, so that is the least of the problems. But there are other viruses, including HIV, which do present a problem and need to be inactivated. Then the whole thing ends in a biobank, and now now comes the interesting thing, and this is fully automated. So I should mention that the way this works is that during the day the technician collects all the samples. Then at the end of the day they are transferred. And then overnight the 384 well plates goes into a robotic setup. And let me see, maybe I can show this to you. I mean, this is how the whole thing works, and essentially this is the same type of setup that you would expect in pharma. So when people do the 1 million compounds for the high throughput screens, so it's essentially the same principle. So we use ultra high density plates so these are microtubule plates that hold 1,536 wells. We use very small volumes. So essentially we all run ELISAS. Now, I mean, the immunology behind it is actually trivial. It's all ELISAS, and but we do lots of ELISAS, the ELISA is running 3 microliters. And so the other interesting thing is that we don't use pipettes, because everything is done using a microdrop dispenser. You can see this machine here. I'm putting, maybe you can see my pointer. So this is a microdrop dispenser, and here there is another, there's a plate washer, and but how do you transfer the plasma sample? We use a technology called acoustic dispensing, and essentially what it does is that it uses ultrasound to produce very small droplets, very precise, 5 nanoliter droplets, transfer from one plate to the other, from the source plate to the destination plate, and so there is a machine called the ECHO that does this. It's also integrated in this entire robotic setup. So the bottom line is that overnight, the system produces 40,000 individual ELISAs. So by the next morning, we have data from 40,000 ELISA points, and this of course allows us to do a lot of things. And so now let me see. I see that something is happening in the chat. So there are probably people who want to tell me something. And right, okay. Okay, so a couple of questions. Okay, did he say COVID does not viremia? Yes, that's what I said. But of course, I agree. There are caveats. Let's say not huge viremia. It's I mean, in the beginning there looked like really there is zero viremia. Of course, in the meantime, we also know that there is endothelitis and that the virus can spread also hematogenically. But I mean, compared to the levels of viremia that you have in truly viremic viruses like hepatitis C, and so, you know, it's not really, the titers are not really comparable. But in any case, we inactivate everything. Yeah. Right. Any other questions?
Can I ask a question?
Go ahead.
So the amount of blood that you need from each person is really minimal. So you could just prick the finger and have enough blood to do it, no, even from children.
Yes, we could do pricks because we need nanoliter amounts, but we have decided to do everything with venous blood, and then we separate the plasma. And the problem is not so much the quantity; the problem is the matrix, because if you have enough, typically what we receive from clinical chemistry are 250 microliters and heparinized blood, and then you can centrifuge and we can extract the plasma, and in essence you can do the whole thing also with whole blood. You don't need actually to get rid of the erythrocytes, but that would require a different type of calibration. So we decided to stick to it, but it would be possible to transfer. So again, it's also a matter of throughput, no? Because when we are handling these numbers, everything has to be streamlined and standardized as much as possible, because the moment you start having differences in different samples, then you need really a huge workforce in order to maintain quality. And here is, this enormous number of samples is dealt by a very small team. It's essentially a PhD student and 2 technicians part-time, and so we a very, very big part of the effort went into making sure that everything is totally standardized.
Thank you.
Right. So, okay. Now let me get back here. So, okay. So then we run the ELISAS, and what we do is that we take 8 data points from so for each antigen, we dilute the plasma. Each plasma sample is diluted over approximately 5 logs, or 4.5 logs, we do unicates. We don't do technical duplicates because they're useless. I mean, first of all, the assay is very reliable, and secondly, the technical reliability we derive by doing a curve fitting, because when you do a dilution series, twofold dilution series, what you end up with is a sigmoid, essentially, and then you can run a logistic regression and fit a logistic curve to the data points, and if there is an outlier, you see it immediately. And a part of our quality control is that anything that cannot be reasonably fitted to a sigmoid is discarded, and this happens, however, very rarely. And and then what is the titer? The titer is what we call the minus log EC50. So essentially, from the logistic regression curve, we infer the inflection point of which is the point where this curve from concave becomes convex. And essentially, the inflection point, the dilution of the sample, this is log 10 dilution of the sample, at which you reach the inflection, is what we define as the titer. So this is very classic humoral immunology, but there are many ways of determining titers. This is a very stringent one because because in order to, first of all, to get a sigmoid, and secondly, to reach the inflection point, you need you need a reasonable amount of antibodies, and so this is how the whole thing is done, and still these are heat maps. So what you see actually here, and I know it's a bit small, but maybe if you're all looking at your computers, you can actually see it, is Well, maybe I can do something about it. Let me just see if I can. Right.
Yeah, that's better.
Yeah.
Thank you.
So this is how these plates actually look like. So these are 1536 well plates. These are the positive controls. And the heat map is essentially the optical density. And so what you see is that here you see the serial dilution. You see of the positive control, and here you have another positive control, and here you have a negative control, again diluted down, and here there is another negative control. And then what you see is that these are the actual samples, and what you see is that some samples are positive, and then we do the 8 dilution steps down. So a column is always a dilution row, and you see that the signal over time disappears, and then you have a lot of negatives or kind of mildly positives. So this is essentially how we run these things. And then the whole thing goes into a analysis pipeline, which I will talk about this in a minute. So for the time being, we have, well, this was the status 10 days ago. In the meantime, we're already at 35,000 people. And because we started this with a completely different goal to find autoantibodies against neurodegeneration, we have been collecting a huge biobank since 5 years. And we have more than 100,000 people in the biobank from 2016 onward. And this was incredibly fortunate because it allowed us to explore what is going on in the pre-pandemic cohort. So how many people do we actually find with positivity at a time where for sure there was no SARS2 running around? And so here we have been looking at 4,500 pre-pandemics and almost 20,000 co-pandemic. And right, let me see, I just wanted to be sure that we don't have more questions. We don't, well, wonderful. And oops. Right, and then so this was the hospital cohort, and then I got a phone call from Beat Frey, who is the director of the blood donation service in Zurich, and he told me, you know, we have a lot of people who donate blood, and we know pretty much everything about them, and why don't you test them as well? I said, yeah, fine. I mean, as long as you can deliver the samples in microdata plate format, we can actually. I mean, the system is so powerful. We can run 40,000 samples a night. So it's so we can actually do it easily, and so from that we received another 1,000 pre-pandemic. So now we are at 5,500 pre-pandemic samples plus 7,500 co-pandemic samples. So now we are really talking numbers. And so what then the question was, what kind of antigens should we look at? And in order to choose, you know. My reasoning was, yes, of course, everybody's interested in the spike and in the receptor binding domain, but you know, one has to be a bit careful. Why is everybody so hung up on the spike? And Tiago and I had a lot of discussions about this, and you know, I think there is a bit of a misconception there. If you want to go for neutralization, or if you want to develop therapeutic antibodies, then of course you will go for those antibodies that have the highest chance of hitting something that is essential for the virus. But that's not really what we're doing here. Here we are using the immune response as a proxy of an infection that has occurred in the past. So it's just a biomarker. So a priori, for me, there is no reason to expect that the immunity against a spike be more predictive than a response against any other of the 20x reading frames of SARS2. So that was something that was worth looking into. And so what we did is there's a collaboration with Volker Thiel, who has developed completely synthetic system of viral reproduction. And so Volker inoculated with this synthetic virus Vero cells, and these express a lot of different reading frames, and maybe not all of them, but certainly a lot of them. And then we just did Western blots with Vero cells that are non-infected, Vero cells that are infected with COV2, and then we just overlaid or developed the blots with serum from our patients with confirmed COVID. These are people who actually had severe COVID, were in intensive care unit, and they have a blasting immune response. And what you see is that you have some background, but in the non-infected cells, but in the infected cells, you actually see two bands that do not occur in the non-infected, and this is the nucleoprotein and the spike. And the nucleoprotein gives actually a doublet, and that is still something that we do not understand 100%. There may be some processing involved, but these are clearly the two dominant bands. But are they really spike and nucleoprotein? So how to be sure? There we did an experiment which I like a lot, which means we just so we take the same plasma sample, but now we spike it with recombinant spike and nucleoprotein. And now the idea is that if the reactivity is mostly the reactivity of the Western blot is mostly due to antibodies against these two proteins, then it should disappear. And this is exactly what happens, because now you have a reaction in solution with a soluble. So the soluble recombinant protein will essentially block the patient's antibodies, and now there is no antibody left to develop the Western blots, and therefore everything is negative. So how does the assay look like, or how does the assay actually perform? For that, what you do is what is called ROC curve, receiver operating characteristics. And these are this is a technique that was developed in the Second World War by the Royal Air Force to detect radars, German radars, and that's why it's called receiver operating characteristics. And essentially, the idea was to determine the sensitivity and the specificity of a detection procedure. And the detection procedure could be anything. As I said, it could be radars, could be an immunological assay, or anything else. And the concept behind it is that sensitivity and specificity are typically reciprocal. So if you want a test that is ultra high sensitive, it may not be super specific. And in certain, and there are certain situations in which you are in which it makes sense to sacrifice specificity for the sake of sensitivity. For example, in the blood bank, you want to be absolutely certain that you are not transfusing anything that may contain an infectious agent, even if perhaps it's not, the test is not super specific. You err on the side of caution. And conversely, of course, there are situations in which you want the opposite. Now, how this curve should be interpreted is that essentially anything, so an assay that, so here you have 1 minus specificity, so, and that would be best specificity, it would be 0, so a specificity of 100%. And here you're looking at sensitivity. Again, this would be 100%. And now the whole thing is more or less inversely proportional. As I said, the higher the sensitivity, the lower the specificity. Now, a terrible assay would lie on the diagonal. So a discriminant that lies on the diagonal is essentially a random predictor. It means nothing. The perfect assay looks like this. It goes all the way up to 1, and then it stays at 1 throughout the specificity values. Now so we ran. So I see that there is a bunch of questions. I will come to that immediately. Let me just finish the explanation of the slide, and then I will take the questions. So so DPO means days post onset. So what you see is that if you test at more than 14 days post-onset, and now we look at three things. We look at the nucleoprotein, reactivity against the nucleoprotein, reactivity against the full ectodomain of the spike, and reactivity against the receptor binding domain. And if you look at this and then I will explain what TRABI is. If you look at 14 days after onset of symptoms, then everything looks just jolly fine. I mean, you get fantastic sensitivity, fantastic specificity. And this is based on, I think, something like 170 positives and several thousand pre-pandemics. And so this would be our ground truth. These are confirmed. So to run these curves, we use confirmed, clinically and virologically confirmed COVID, as well as people whose blood dates from long time before the pandemic. Now, if you go at between 7 and 13 days post onset of clinical symptoms, then now things start looking murky. So now you see that actually you no longer have a perfect discriminant, and now you have to decide. If you want to have top specificity, you have to set a cutoff of sensitivity that will be actually pretty bad, and vice versa. So now we are exactly in this conundrum where you need to make informed decisions about what it is that you're actually looking at. And now, what is TRABI? TRABI is what I call the tripartite antibody blood assay, and tripartite means the following. So we run three different ELISAS for these three proteins. And now the idea was, okay, each data, so each antigen is measured at 8 different concentrations. So altogether, each sample is tested on 24 ELISA, individual ELISA assays. And what I was thinking is, what you end up with is a multidimensional vector that, and each one of these assays have their particular strengths. For example, we know that the nucleoprotein is more sensitive than the spike, but we also know that it is less specific. You get cross-reactivity with the nucleoprotein. And so the idea was, okay, can we actually create a metric that will incorporate all of this? And this was done with the help of some fantastic mathematicians, and David Lamparter from the lab of Johannes Xenarius of the Swiss Institute of Bioinformatics have actually worked on this. And what they have come out with is a machine learning approach using what is called quadratic discriminant analysis. And essentially, what this builds is a unitary measurement, and this is actually this TRABI assay. And you see that if you actually combine the three antigens, you do actually get a better performance than with any of the single antigens. So in principle, this works. And then what we did, and this is very funny, we actually compared our assay to everything that was on the market a few weeks ago. And I am exceedingly pleased to report that our assay performs better than everything, including the Abbott, Roche, all the giants, the diagnostic giants, but also Diasorin. And what I can tell you is that Urimmune is by far the worst. So I think, so the Urimmune assays, I can only advise you to just don't touch them with a 50-foot pole. But again, I mean, there is if you go at late time points, then actually everything works. And the problem is only when you are looking at early days. And of course, the reason is actually biological. It's because the immune response takes time, and at the early time points, you still have very little immunoglobulins around. Right. So okay. So okay, here there is Luis is asking why does the background in the control goes away? That is a good question. I don't know. We need to think about it. yeah, we need to think about it. I mean, it may be just as simple as a difference in the time of exposure. I really don't know. I need to ask the person who has actually done this work, who is Elena De Cecco, is a very, very talented Italian postdoc who joined my lab a year ago, and she has done all of these essays. Now, then I have another question. How do spike plus RBD compare to TRABI? I don't quite understand what...
I guess this is the Florian-Kramer protocol, no, Bruno? Using first RBD and then spike as a validation to compare it to TRABI. Is that what you mean, Bruno? I don't know.
Sorry. No, sorry. I just meant in your layout to remove the nucleocapsid. If you ever tried the combination of two without going for the three.
Okay. So so we didn't do that. I cannot tell you. Right. So, okay. So something else that I think bolsters the idea that really the problem with the degradation of the assays at early time points has something to do with the development of the immune response is shown here, because here, we have some of the patients are repeat, and essentially, so approximately 5% of all our samples are actually from patients from which we already had some samples. And the reason is actually a software glitch. Originally, I wanted to have just one sample per patient, but then it turns out that the software that picked the samples had a bug, and so it turns out that approximately 5% of our samples were repeats. But then in the end, I was actually very happy about this, because it turns out that this allows us to look at a bunch of other things. So, so here we have been looking actually longitudinally at individual patients, and over time, days post onset, and you see, I mean, what is of course to be expected. You see the course. This is the log is 50, so the titer goes up over time while well, I mean, it's actually pretty obvious. So the bioinformaticians eventually had this brilliant idea of calculating the posterior probability. Now, the posterior probability, and this is really, I mean, the mathematics behind this is actually it's pretty complex, and I only understand it to some extent, but not really all the details. And but the posterior probability is essentially, there is a prior probability, which is the seroprevalence. The actual seroprevalence is the prior probability, and then the posterior probability incorporates essentially the performance of the assay, and essentially it is the probability of any individual to be seropositive as modeled by the distribution of the condition positive and the condition negative. So all the data that I have shown you before, this type of curves go into the calculation of the posterior probability. So now what we are doing here is the following. Here we are looking at spike, titer anti-spike, titer anti-RBD, and we are calculating the posterior probability using this quadratic discriminant analysis in the cohort of the hospital patient, University Hospital Zurich was that. And those are heat mapped. And now what you see is actually wonderful. You see that, I mean, for me, first of all, of course, the highest posterior probability, you find them in the collective that is double positive for RBD and for S. That is not a big surprise. And we have also the same thing for spike and nucleocapsid. But the amazing thing, and that is perhaps not so clear from this slide, but the amazing thing is that the posterior probability essentially is either 1 or 0. you see that there are hardly any intermediate levels. It's really either we are in this regime or we are in this regime. And now this is wonderful because this means this gives a very high confidence that we can assign strong probability values to our patients. So the outcome of our assay is that we do not you know, most lateral flow assays, and so they end up telling you, yeah, you are positive, you are negative. We don't do that. We give you a probability value. We say, okay, your posterior probability is 0.95, it's 0.05 or whatever. So this is essentially what we're doing here. And this is the same exercise done for the blood donation service. This is the most important slide of the entire talk, and this is a big surprise. So having established all these methods, we now ask what is the prevalence in the population. And again, we have two separated cohorts. We set the hospital patients and the blood donation service, and so the prevalence is extremely low. It's extremely low, and you see it hovers around 1.2, 1.3%. And what gives me a lot of confidence, you know, I showed this data, and then the epidemiologists all jump at me and say, yeah, you know, this is not representative, and how do you know that the population in Zurich? But, you know, these two populations are completely different. I mean, these guys are sick, these guys are healthy, and the age distribution is different. I will show you that. But in the end, we are talking about very, very similar values. So at this moment, I am pretty confident that the prevalence is really low in the area of Zurich. And this is surprising for a number of reasons. First of all, Zurich is a very international city. There is a huge airport. And so it is amazing that we have I mean, assuming that we are really looking at, we are really identifying people who had been exposed to the virus, it is surprising, given you know the internationalism of Zurich, it is surprising that we have so few of them. The other big surprise is that we had a catastrophe in southern Switzerland, Ticino, but also in western Switzerland and Geneva. There is very large numbers of people who got sick. Switzerland has never tried to block intercantonal traffic, so people were always free to go from one place to the other, and yet the area of Zurich has remained obviously pretty unscathed. The other big surprise, and this really got me completely, I mean, I think it's crazy, is look at what is happening here. In the second half of March, so we are always looking at 15 days, so first half of the month, second half of the month. And you know, it's the second half of March, that's where we start seeing positives. Here are all the pre-pandemic, 4,500 pre-pandemic and nothing. So things go up in the second half of March, then they climb very quickly at this level, and then they stay like that. This has never changed. So now we are, the data from the second half of June are not in yet, but so far what we can see is that there is no real increase. So what does this mean? I think there are two possibilities. One is that there have been no infections anymore, so the lockdown was extremely effective, and therefore, you know, in a way, the percentage of seropositives should be the cumulation of the number of infections. So it should be essentially the integral of the acute infection curve. And so if it is stable, this means that there are no more infections, or the alternative is that there is waning, the seropositivity is disappearing, and the rate of waning is in equilibrium with the rate of new infections, and therefore the result is that you have a steady state. So these are the two possibilities. They are non-exclusive. I mean, it could be that there is a bit of one and a bit of the other. I honestly don't know what the reason is. I can only speculate. Yeah, but then of course the question was how representative this is, and so first of all we looked at the age pyramid of our collective. This is a collective from the patients, from the hospital patients. So here we are looking at the entire collective, and this is divided by 40. And then here these colors indicate the seropositives, and this is actually actual numbers. We decided to present the data in this way in order to make it more legible. But of course, there is a massively higher number of seronegatives. But what you see is that there is no age class that has a particularly strong accumulation of seropositives, and also the gender is pretty equally distributed. And this is the blood donation service, and it's the same thing. So what is missing from both is, of course, the children, because the cutoff is 18 here. That is when people get into the university hospital. The younger ones go to the children's hospital, which we don't have access to. And then there is in the blood donation service, the same thing. You can only donate blood when you are when you're a legal adult, and also there is a cutoff at 65 where people are no longer allowed to donate blood. And don't ask me who these guys are who are still donating blood in their 70s. I have no idea. It's actually not legal, so I'd rather not know what is going on here. But but essentially this is the distribution. And then we also looked at where these guys come from, and half of them come from the city of Zurich, half of them comes from the canton of Zurich. So this is actually the canton of Zurich around here, and then we have very few people from extra-cantonal, and the reason is insurance. The insurance in Switzerland will typically not pay if you get treatment outside of your home canton. It's a pretty crazy thing, but the result is that we have mostly local people, and that, in my opinion, makes this study more powerful, because now we have really, I mean, you have to say, I mean, the city of Zurich has 480,000 inhabitants. We have tested 35,000. So we're talking like 80% of the entire population. And I think that this kind of depth is something that I have not seen in other studies. Okay, there is a bunch of questions that I have seen. Now, let me see. Let me go to the chat. So, what about... yes, so I think there are a couple of questions here about the titers reduce after day 40, stay stable at 70. Yeah, we'll see what happens in our collective. I don't think we have enough data to really say that yet. And the other question is, yes, whether the waning may be different for different antigens. Yes, of course, these are all things. And I should also mention that I want to look at more antigens. So far, we have focused on these three for many reasons, including the fact that the name TRABI is very, let's say, melodious, and so it could become Quabi or something like that if we have four. But we're starting to look at additional antigens as well, and here we have been looking at where these patients come from which department, and you see actually there are two peaks. So these are all the departments of the hospital. So neurology, internal medicine, oncology, gynecology, and so on and so forth. And you see actually that they come from pretty much any department. There are only two peaks, and this is infectious diseases. So these are the people who were hospitalized really because of COVID, and internal medicine, which also had some people who came in because of COVID. But actually, the surprise is that these are the guys with diagnosed COVID, and but the vast majority are guys who are seropositive, but they have never had COVID. So these were not clinically detected. These were in principle asymptomatic. So now one of the next thing that we need to do is to interview these people and to ask them what exactly, whether they had anosmia or and so on and so forth. And by the way, I should like to just advertise the paper that we have just received acceptance in the Lancet that was done by my colleagues in the clinical neuropathology service, and specifically Karl Fronzek and Daniel Kirschenbaum, and they have essentially discovered the anatomical basis for anosmia in COVID, but that's another story, and they should talk to you. You should invite them for another webinar. It's a fascinating story, and but I don't want to talk about it, but you will soon read it in the Lancet.
That's right, thank you.
So this is essentially the situation, and so just one further point about the posterior probability. This mathematical treatment is unbelievably powerful, and I think that this is the best representation. Here again, we have mapped the posterior probability in pre-pandemic versus pandemic samples, and you see that even if the log is 50 for individual proteins, spike, RBD, and nucleoprotein is sometimes overlapping. So we have also pre-pandemic people with a pretty high, I mean, particularly the nucleoprotein. You see, I told you the nucleoprotein is not very specific. So we have also pretty high titers against the nucleoprotein in pre-pandemic samples. But if you map the posterior probability, I mean, it's like day and night. You see, these are all white and these are black. So there is really real power in doing these very accurate, very deep analysis with all these different ELISAs and really combining them and doing data treatment. You can then really discriminate false positives from true positives. So again, so what is the story with the pre-pandemic? I mean, it's interesting, no? I mean, you have people from 2016 and they have sky-high titers. You know, when we're talking about, I mean, let's face it, I mean, when you have dilute titers, I mean, here 10 to the minus 3, the inflection point here is around 10 to the minus 3. I mean, the inflection point at a dilution of 1 to 1,000, that is essentially what 10 to the minus 3 says. I mean, these are very strong titers, and but these people are from 2 years before the crisis. So what is going on? This is ultra interesting. So a couple of things. First of all, yes, you have high titers in the ELISA, but if you do the Western blots, they just don't work. I mean, most of them. I have to say that we found one that worked, but particularly the RBD. If you do the Western blots for the RBD, you see nice signals in the what I call the co-pandemic or the COVID, actually the confirmed COVID samples, but the pre-pandemic, you see actually nothing. And so this to me, so the fact that it doesn't work on the Western blot to me, but it works in the ELISA, means that perhaps we are talking about conformation or discontinuous epitopes or some kind of epitopes that are destroyed when you boil the stuff in SDS. The other way to look at it is to do competition ELISA. And now the principle is the following. If you, I see that I am running over time, so I was planning to talk only for 20 minutes, but I get carried over. So
I think it's okay. I think it's okay. People will be happy, and you've been super pedagogic, so I think it's very nice.
All right. No, but I'm almost finished. Yeah, but you have to, because I have this tendency of going on and blather away like Fidel Castro for several hours. But so I will try not to do this today. Essentially the competition as ELISA, I think, is a wonderful thing, because what you do. So essentially, what you do is if you. So first you do the usual titration, and you get your sigmoid. Now the thing is, let's just do the Gedanken experiment that you do. You spike your plasma with the antis, and now what? And then you run the titration curve again. And now what happens is that the entire curve is shifted And because, of course, you have less antibodies that is available for binding to the solid phase. Now, the thing is, the shift is a measurement of affinity. And the reason for that is the following. Now, let's imagine a titer can, an antibody titer can come about in two ways. Either you have a boatload of low affinity antibody that way, or you have very little high affinity antibody. The titer will not tell you which one is true. You can get exactly the same titer from low concentrations of high affinity antibody or high concentration of low affinity antibody. So, but now let's assume you have a lot of low affinity antibody. Now you spike in your competing antigen. You cannot titrate it away because there is too much of it. So, the result is that your curve will not be shifted. It's a bit counterintuitive. If the antibody is high affinity, now you put in your spike, and because, yeah, it's high affinity, but there is much less of it, so it will be competed away. So you can, so the competition is a measurement of the affinity, and this works extremely well. And so we did this experiment, and again, I will make it very short, but the interesting thing is that you get a beautiful competition with, you know, here we did everything. You know, we compete RBD with RBD, so RBD soluble, immobilized with RBD, RBD soluble, immobilized with S, competition with RBD, and all the permutations. And essentially the results is that if you get beautiful competition with the COVID samples, but the pre-pandemic, even if they have a high titer, they don't compete at all. And this, for me, is a very strong evidence that the affinity of the pre-pandemic samples, even if the titers are high, the affinity is very low. And so these are inferior quality antibodies, and they're probably cross-reactive. And then, of course, the question is, are cross-reactive to what? I mean, to COVID-1, to other things, and this is something that we are doing at the moment. I should also mention that we are looking also at asymptomatic versus convalescent, but this is a bit preliminary. All I can say at the moment is that the antibody titers are very similar. I'm very interested in the potential difference in affinities between people who have undergone a COVID infection and know nothing about it, they never had clinical signs, versus people who are severely sick. And the only thing I can say at this moment is that there appears to be huge differences in affinity, but let me tell you just one thing. I would say a final thing is how do you measure affinity in a polyclonal population? I mean, there is a problem here, no? Because, you know, affinity, you can do, if you have a monoclonal, you can do BIACOR or kind of SPRs. There are many ways of doing this, and you can do kinetic of a dissociation constant, and all of this is very, very well established and very reliable. However, plasma is a different animal because you have 1,000 different antibodies in there. They all have different affinities. And in fact, I don't know really of anybody who has been able to reliably determine affinity in plasma using SPR. And so we have been trying to address this using this competitive ELISA. This is kind of a poor man technology, but it works. And it works because you have immunodominant epitopes. No? So you have high affinity, the highest affinity antibodies will trump everything else. And so in a way, you can actually work with this. But then eventually a real breakthrough was to use an instrument made by a company called Fluidic Analytics, and they use microfluidics to essentially determine the hydrodynamic radius of the antigen-antibody complex, and then they measure the dissociation rate at a single molecule level and using sophisticated detectors. And so this we have done, and the results are pretty congruent with those of the competitive ELISA, and this is work in progress, but I'm very excited. I think that using this microfluidics thing, we can really do precise affinity measurement of this complex gemisch, which is a polyclonal response. Right. So I'm looking at the chat, and I see that there are a couple of questions about the subclasses. We haven't looked at subclasses, and then which within symptomatic people do you find relationship with antibody titer and pathology? At this moment, not between titer, but with affinity. And again, this is super preliminary, and don't nail me on it because it may still all fall apart. But from a relatively small collective that we have looked at, I have a feeling that the asymptomatic people have a much higher affinity. I mean, 100 to 1,000 times higher overall affinity than the people who have undergone severe disease. But again, you know, these are small numbers, so the whole thing may still change. Right. I think that, this is, these are essentially these graphs that are being produced with this microfluidics machine. So essentially, so these are density probability distributions of derived from single molecule measurements, and I think I'll stop here, and I want to acknowledge the people who did the work, and really Mark Emmenegger is the PhD student who really pushed this project amazingly, and I have to say he really worked day and night. I mean, literally day and night. And I mean, we had really sessions that went on until midnight, and then we started at 6 o'clock in the next morning. I mean, the whole thing was, but you know, I mean, I would realistically say that this collection of 35,000 samples normally would have taken us 2 years under normal condition, and that the whole thing was done essentially in 2 months. So great kudos to Mark and Elena Dechecco, who has been has done all the immunochemistry related to the Western blot, the competition assay, all these things. And then David Lamperter and Raphael Jacat are the 2 bioinformaticians who are really very insightful. And you know, what I really loved about this is that sometimes you know, some biologists, I mean, none of those present here, but some biologists regard bioinformaticians as kind of the guys who will calculate the p-values for us. And you know, this, first of all, it's a bit disrespectful of the bioinformaticians, but in reality, you know, if you have somebody who really understands the math and understands the biology and is really passionate about developing methods, then amazing things happen. And this is really what these 2 did. And then Matthias Schneider is a PhD student at the University of Cambridge with Thomas Knowles. He was stranded in Switzerland when could not go back to the UK, and so he joined us, and he did all this microfluidics measurement, and this was actually wonderful. Right, so thank you very much.
This was a fantastic seminar, and you were super pedagogic. I think it was really useful for people from very different fields, and we hope to welcome you to IGC in presence in the future. Thank you very much. Bye-bye.
Thank you, everybody. Take care, goodbye.
Bye.